Okay, hi everyone. Today I'll be presenting the paper Direct Preference Optimization. Your language model is secretly a reward model. And this paper proposes a new method called Direct Preference Optimization, um, which simplifies how we train language models from human feedback instead of using reinforcement learning. So, large language models are trained on huge data sets collected from the internet. And because of this, they learn a wide variety of behaviors. Some are desirable and some are undesirable. For example, your coding agent AI should understand common mistakes in coding, but should generate correct code when responding to users. So, to address this, researchers align models with human preferences, meaning that we train them to produce responses that humans judge as more helpful, safe, or accurate. And the most common approach for this is reinforcement learning from human feedback, or RLHF. So, what is reinforcement learning? In reinforcement learning, the model's goal is to develop a strategy that will give it the most reward overall. Instead of learning from labeled examples, like in supervised learning, reinforcement learning learns by trial and error. So the model will take an action and then observe the results, and then it will receive a reward or penalty and then update its strategy to get more reward in the future. Even though this works well, it introduces a lot of complexity. So, how the reinforcement learning pipeline works is that we first fine-tune a base language model using supervised learning. And what we do here is we just use human-written examples to train the language model. And then next, we will train a reward model to predict which responses humans prefer, which we then use to optimize the language model using reinforcement learning algorithms such as PPO, which is used to update a policy while preventing it from changing too much at once. So this process is computationally expensive. It's also difficult to tune and often unstable. So the paper proposes a key question. Can we achieve the same alignment objective without reinforcement learning? So the three key ideas of the paper. First, the authors show that the language model itself can represent a reward function. And secondly, they demonstrate that the optimal solution to the RLHF objective can be derived analytically, which means instead of solving this by trial and error, we can directly find the best policy with one formula. And then finally, they show that we can train the model by treating preference learning like a binary classification problem that basically asks which response is better. And this leads to the main algorithm introduced in the paper called Direct Preference Optimization, or DPO. So the main contribution of this paper is this algorithm called DPO. Instead of training a reward model and then applying reinforcement learning, DPO directly trains the language model using preference data that human or AI labels. The algorithm transforms the RLHF objective into supervised learning loss, which makes the training process significantly simpler and more stable. And previously, when we used reinforcement learning, the reward models that are trained to optimize to train to use to give rewards to the actual language model often has errors, and reinforcement learning is often unstable. So supervised learning is much more stable. So here's how the human preference data works in DPO. DPO learns from pairwise preference data. For each prompt, we generate two responses, and the human or an AI annotates which response is better. And then we label the preferred response as the preferred one, and then label the rejected response as the rejected one. And then the training objective for our language model is to increase the probability of um, generating the preferred responses relative to the rejected ones. So the key theoretical insight of this paper is that the reinforcement learning objective has a closed form solution. By analyzing the KL-constrained reinforcement learning objective, the authors showed that the reward function can be expressed using the ratio between the trained model and a reference model. So a reference model could be the base model that we trained in the beginning, and the trained model would be what we continue to optimize during DPO. This means that the language model itself implicitly defines the reward. And because of this, we no longer need to explicitly train a separate reward model. Using the theoretical derivation, the authors transform preference learning into a binary classification problem. The loss function increases the probability of preferred responses and decreases the probability of rejected ones. The model is also regularized to stay close to the reference model. So we don't want it to deviate too much from the base model. Because the loss is differentiable, we can train the model using standard gradient descent instead of reinforcement learning, which is much more stable. So we talked about the reinforcement learning process, and now let's talk about the DPO training process, which becomes a much more simple pipeline. First, we collect a data set of prompts and preference comparisons. So yeah, this could be labeled by humans or AI, and then we select a reference model, usually the supervised fine-tune model. And then, so the supervised fine-tune model is the base model that we train in the beginning. And then finally, we optimize the DPO objective directly on the preference data, which produces a model aligned with human preferences without requiring reinforcement learning at all. And here's how the authors evaluate DPO on 3 different tasks. First, they do sentiment controlled text generation using the IMDb dataset. And then they also did summarization of Reddit posts and as well as helpful dialogue generation using the Anthropic HH dataset. They measure performance using reward versus KL trade-offs and preference win rates evaluated by GPT-4. They compare against PPO-based PPO-based reinforcement learning, supervised fine-tuning, and best of N sampling baselines. So the results show that DPO performs as well or better than PPO-based reinforcement learning across several tasks. It also produces a better reward versus KL trade-offs, which means that it achieves higher reward while staying closer to the reference model, which is an important metric because we don't want it to deviate completely from the base model. And then another key result is that DPO requires far less hyperparameter tuning compared to reinforcement learning models. So obviously less computationally intensive. Some critiques of the method, some strengths that the paper has is that it significantly simplifies the reinforcement learning pipeline while maintaining competitive performance, and the theoretical derivation is also very well justified. But however, there are some limitations. The method still requires high quality preference data sets, which can be expensive to collect. Like you either have to have humans label them or ask another LLM to label. And the approach also assumes a particular statistical model of preferences, which may not always be true. Like real human preferences may not perfectly follow the may not perfectly follow the reward of that response. And then finally, the experiments are limited to models up to about 6 billion parameters. So, yeah. Now some discussion questions. Thank you.